Hello everybody, I know I haven't made a video in a while. I have been busy with school. As you can see, I made a little bit of a modification with the help of my dad, and we got this part stabilized quite a bit more than it was before. That idler sprocket that was over there was kind of over tensioning it, and it was making the whole thing twist, which was not good. I had a chance to sit down and program this off of the potentiometers. Right now it's just using a simple joint move program. So let's jump right into watching the program run, and I will explain how it works along the way. So the program is running right now. It starts off in the manual move, which is the same thing as I showed you. I've got these buttons, and they toggle between moving in the different directions. But now I have two more buttons. One, I have an e-stop, very, very important. It saved me right when I was first testing this. And then this is the button that changes between manual and automatic mode. So when I press this, it'll start executing a little program, and I have three different points that it will move to. So right now, this is moving all on its own. So there's point 1. There's point 2. And there's point 3. Now, at any point during the cycle, I can press the manual mode switch button, and it will return me to automatic control. And I just tap the yaw button. Whoop. I have not implemented the yaw yet into the program. I've only been working on this. I have the manual control for it, but I don't have the variable set up yet. So now that it's back in manual move, I can go back to pressing the button. And I'll show you, this is the auto button. So when I press this auto button, I can press this at any time, and it'll stop. If I press it again, it'll go back to doing the program, and it'll start back from the beginning. So, for instance, now it's going to point 2. If I stop it, and then I start it back up, it'll go back to point 1 first. And I got so I did get my 3000 milliamp battery, and it's hard to say, but I think that there was definitely an improvement in the speed of the robot. So definitely glad that I got that. One other thing that you can see here, or maybe not, I added on some white lithium grease, which was found at Home Depot in the greases, lubricants, and fun section at Home Depot. And with the worm gears have really high friction, and friction means heat, and heat on plastic means melted plastic. and I put this on the worm gears and also the bevel gears, and there was an immediate improvement in both the noise that they were making and obviously in the wear and tear on the worm gears themselves. So this was pretty cheap. I don't remember exactly how much it was, but I think it was probably under $10. And you barely need any of this to get the job done. So definitely a good thing. Now, how does this actually work? Well, in the program, I used the typedef command, and I created a structure. The structure contains all of the variables for the degree values that I want for, say, the position. So I create the typedef for the position, and then the position has, say position 1 dot shoulder degree is equal to 45, and it basically just goes through like that for the 3 different joints that I have programmed in. And I create a temporary point called target position, and when I call, in order to make it do the movement, I have a 2-step process. First, I have a function. The function is a move position function, and you pass it the structure for the position. It then takes that position and then it copies over the 3 different variables to the target position variable. All the position variables are global. And after copying the copying those to the target position variable, it creates there's another set of global variables which are booleans, and they represent whether the movement of a particular joint is done or not. Once the joint is done moving, it's set to true. So after it, right before it starts, then I've got, let's see here, how to explain this. I have 3 different tasks, 1 task per joint. That lets all 3 joints move independently and have independent control over when they stop. Once the task finishes, or right at the end of the task, it changes the status of the Boolean variable for whether it's done moving to true. And then in the function itself for the move position, it starts all 3 tasks, and then it has a wait command, or it has a while command, and it's while any of them are false. So while any of the joints are still moving, wait to go to the next step. So you can see that some of the joints will finish moving before the others. Well, that just makes it so that they all get their chance to move and finish moving before it moves on to the next position. In the task itself, for each joint, it takes a measure of the current potentiometer reading. Then it uses a formula to calculate out where it needs to go for its target position based off of the degree value that it was fed. The formula converts the degree value into a potentiometer value. Then it checks to see whether the target value is less than or greater than the current value, and it moves the motor in the appropriate direction until the values are equal. And from the looks of it, it's actually pretty accurate. We'll see just how accurate it gets once I start taking things to the next step. as I mentioned, right now I'm doing joint style control, which is the most basic. I'm telling it a degree value that I want it to go to, and then the joint will then go to that degree value, but that doesn't give good control over where the tool control point is, because you have to manually figure out where the heck everything is based off of that. Eventually I already have the formulas for this, but I know how to take joint values and convert them into Cartesian coordinates, and I know how to take Cartesian coordinates and convert them into the joint values, which can then be converted into the potentiometer values, which can then be used to set the position of the robot. So that'll be the next step. Thank you for watching. We'll let it run one more time just because, assuming that it's still running. There we go. Woohoo!